Hello, everyone, and welcome. My name is Jessica Williams, Programs and Community Partnerships Manager at Chabot Space and Science Center, and we are thrilled to bring you another exciting program live to your homes this evening. Thank you for tuning in, everyone. Tonight, we have with us a familiar face, Gerald McKeegan, who will talk with us about the Perseverance rover as it prepares for landing on Mars on February 18th, 2021. Before we get started, please consider making a donation to help us make these programs possible. These events are fueled by you, our community, and right now we need your help to create STEM learning opportunities for our community at home. In less than a minute, you can make a difference by donating on Facebook or at chabotspace.org. We ask that you please take a second, click that donate button, and make an impact by supporting STEM education if you can. And now I would like to introduce to you Gerald McKeegan. Gerald McKeegan joined Chabot in the year 2000 as a volunteer and adjunct astronomer. Gerald serves on the Chabot's JPA Board of Directors and is a member of the East Bay Astronomical Society. He holds a Master of Science degree in Space Studies and has over 40 years' experience working in the space industry, where he was involved with numerous spacecraft projects, including the Space Shuttle Cassini. Oh, sorry. Mars Reconnaissance Orbiter, Mars Insight, Solar B, Juno, and many others. In 1988, he was awarded the NASA Silver Snoopy Award by the NASA Astronaut Office for his work on support of the post-Challenger Space Shuttle Return to Flight program. He also had Chabot's Near-Earth Asteroid Search and Tracking Program and has made more than 2,000 asteroid observations using Chabot's 36-inch telescope. Thank you, Gerald, for joining us.
Hi there. How you doing?
Good, I'm good. How are you doing?
I am doing great. I'm up here at the Chabot Space and Science Center. I'm in one of our exhibit halls. This is the exhibit area called Going the Distance. And if you look behind me, you can see one of our exhibits here. We have a very large Mars globe. And when we are open, you can come up to Chabot and take a look around the Mars globe and actually see all of the landing sites. We haven't marked the Mars 2020 Perseverance landing site yet because it hasn't happened. It won't happen until February 18th. But by the time Chabot reopens later on this year, I'm sure we will have a marker on our big globe up here showing you where it is. Um, as Jessica said, please be sure to help us out by clicking on those donate buttons. There's one on the Facebook page. If you're watching Facebook, there's also one on Chabot's website, chabotspace.org, and you'll see a donate button up at the top of the page. We really need that to keep all of our virtual programming going and also to make sure that the facility is up and running when the time comes so we can reopen for the public. So anyway, my task tonight is to tell you a little bit about the Perseverance rover landing the Mars 2020 mission, tell you a little bit about how it's going to get there, what the landing sequence is going to be like, a little bit about where it's going on Mars, and so on and so forth. But before we do that, I wanted to take a moment to pause and reflect on an important anniversary. Yesterday was January 28th, and it was the 35th anniversary of a very important event in the history of space flight. Yesterday was the 35th anniversary of the Space Shuttle Challenger accident. 73 seconds after the Space Shuttle Challenger took off, it exploded and all of the crew on board perished. So I just want to take a few minutes to talk about that crew. Here's a photograph of the Challenger crew. And you'll have to bear with me if I struggle a little bit as I go through this. I had some personal involvement with this event, and it still brings up a lot of emotion for me. So just bear with me here. But I wanted to introduce each of these individuals here. So on the left, we have Ellison Onizuka. Ellison was born in Hawaii. Before joining NASA, Ellison was an Air Force test pilot. He was an avid runner, And of course, being from Hawaii, he liked fishing. Down in front of him is Mike Smith. Mike was the mission pilot for the Challenger mission. So he sat in the right seat in the cockpit. And before joining NASA, Mike was a Navy test pilot and also a flight instructor. And as a hobby, Mike liked to do woodworking. Uh, Behind Mike, Krista McAuliffe, the teacher in space. Krista was a teacher in New Hampshire. And when NASA decided to start the Teacher in Space program, she signed up and she was eventually selected to be the first teacher in space. So her teacher in space activities was supposed to be part of this Challenger mission. Down in front again, Dick Scobie. Dick was the mission commander on the Challenger mission. Dick had been an Air Force test pilot before joining NASA. He loved flying. And one of the things that Dick did when he wasn't being an astronaut with NASA is he trained the pilots of the Boeing 747 that NASA used to transport the space shuttles back and forth between California and Cape Canaveral and so on. Some of you may recall that they used to mount the space shuttle on top of a big 747 and it would fly across country that way. And Dick's job was to train the pilots who flew that 747. Behind Dick is Greg Jarvis. Greg was an engineer who worked for Hughes Space and Communication. He was not a NASA employee. He was actually what we call a payload specialist. He was employed by Hughes Space and Communications, and he was on the mission because they were going to do a practice where they had a satellite called the Spartan. And the mission was to release the Spartan into space and then go retrieve it again. And so he was there to help out with that. Greg was one of the musicians on the space shuttle on the Challenger mission. He was a classical guitarist, so he was very musically inclined, as was Ronald McNair. Ronald was a mission specialist on Challenger. Ronald was a physicist and he specialized in lasers and spectroscopy. Uh, he played jazz saxophone. And in addition to all that, he had a black belt in karate. And then lastly, we have in the background Judy Resnick. Judy was another mission specialist. She was an electrical engineer before she joined NASA. And Judy was yet another musician on this flight. Judy played classical piano. So this was the crew. And yesterday was the 35th anniversary of this mission. Very sad event in the history of human space life, at least for the United States. Now, as sad as it was, there was one good thing that came out of this. After the accidents, the families of the astronauts got together. They wanted to do something to honor these astronauts. And so they came up with the idea of starting a program called the Challenger Learning Center. And these would be learning centers around the country where people could go and learn about spaceflight. And we have one of those Challenger Learning Centers right here at the Chabot Space and Science Center. You can sign up and fly a mission. You can either work in mission control or we have a simulated spacecraft and you go inside the spacecraft and you fly a mission. And the teams in mission control and the teams in the spacecraft, they coordinate with each other. They solve problems, figure out how to get the spacecraft into space. They actually fly simulated missions to Mars or to retrieve a satellite or what have you. And it's a lot of fun. You get together with a whole bunch of people and fly the mission. It can be a little tense at times, but it's a great fun thing to do. So, after Chabot reopens again later on this year, that's something you might want to think about looking into is the Challenger Learning Center. Bring your friends and fly a mission. Okay, well, let's go on to the main part of the program here. So February 18th, almost 3 weeks from now, uh, the Mars 2020 mission, the Perseverance rover, along with the Ingenuity helicopter, are going to land on Mars. So I want to talk just a little bit about that mission and tell you how it all is going to work and get you prepped because on February 18th, which is a Thursday, starting at about noontime, we are actually going to have a program here at Chabot where we are going to follow the mission and kind of provide commentary as the landing sequence occurs. We're going to watch NASA TV together. We're going to answer your questions. And then after the landing, we are going to come up live here. We'll have three experts, a couple of Chabot astronomers, plus a representative from NASA who will answer your questions. So that's something you can look forward to. But it'd be good if you could learn a little bit about the mission beforehand, and that way you will have some really good questions to answer. So let's get started here. So let's go back to July of 2020. And that's when the United States, United Arab Emirates, and China all sent spacecraft to Mars. So we sent a whole fleet of spacecraft to Mars. The United Arab Emirates sent the Hope mission, which is an orbiter that would orbit around Mars. China sent a small rover called the Tianwen-1. Um, and then the one we're interested in, of course, is the Mars 2020 mission carrying the Perseverance rover and the Ingenuity helicopter. All right. So where are they going? Well, obviously they're going to Mars. So this is the Hubble Space Telescope image of Mars. And I want to call your attention to one region up here. You see kind of a triangular shaped region right here. This is a feature which can be easily seen even with small telescopes here from Earth when Mars is closest to the Earth. You can see it pretty clearly. And that region is called Syrtis Major. And up near the upper right part of Syrtis Major, that's where the Perseverance rover is going to land. So here's a kind of a closer view. This is taken by the Mars Reconnaissance Orbiter, which is a spacecraft orbiting Mars right now. And the region we're looking at is kind of right in here. So right about there is where the Jezero crater is located. And the Jezero crater is the target for this mission. And I'm going to show you why it's the target here. Here's a closer view of the crater. And this is a false color image. It's used to kind of analyze the geological composition of the surrounding terrain. But one of the interesting things about this crater is it's quite old. It's billions of years old. It dates back to a time when Mars had a much thicker atmosphere than it has today, and it had liquid water on the surface. And we think part or all of the crater was actually filled with water at one time. In fact, we're sure that at least part of it was filled with water at one time. It was a big lake. Now you see a little circle here, or an ellipse actually. This is the target area where the Perseverance rover is going to land. We call that the target ellipse or the landing ellipse. And the reason we picked that, I'm going to go into a closer view here. This is a true color image of that same region. And you notice that there's kind of a fanned area right here. This is the bottom of the crater. And like I said, several billion years, a few billion years ago, this crater was full of water. And the water came into the crater on this old river channel. You can actually see the river channel right here. And you can see that the river had cut a notch, if you will, through the rim of the crater. The rim is about 1,600 feet high. And debris in the river spilled out into the lake and created this delta region, like an alluvial fan. Um, and that's why they picked this location. We think back when Mars had a thick atmosphere and water on the surface, that the conditions were right for life to have possibly taken root on Mars. And so the thinking is that this river has all kinds of silt and sediments flowing down the river and being deposited in the lake in this region here. If there was any life there, that would be part of what was deposited in this region. So that's the reason for targeting this part of Jezero crater. The mission has four primary objectives. First, looking for signs of habitability, looking for signs that yes, there really was water there. Yes, the chemistry of the soil is right. So it would have been able to support life had it existed a long time ago. Maybe even it still exists. So along the same lines, they're going to be looking for biosignatures, actual signs of past or present life by chemical processes, by physical remnants, what have you. They're going to try to see if they can actually find any indication that life once was there and maybe life is still there. Another important mission is to collect samples of rocks and soil and store them on the rover. And then on a future mission, a spacecraft will go to Mars and actually retrieve those samples and bring them back to Earth. So scientists on Earth can study those samples directly rather than having to do it remotely with the rover. And then lastly, they're going to do some testing. If we send astronauts to Mars someday, they're going to need oxygen, they're going to need water, and so forth. And they need oxygen not only for breathing, but also to use as a fuel for a return trip. And so the Perseverance rover has some equipment on it that will allow them to test the production of oxygen using soil or moisture that might be in the soil and so on. Different ways of producing oxygen so that they know whether or not they're going to be able to do that for future human missions. So that's where they're going, and that's what the purpose is. So let's talk about how they are getting there. So this is the Mars 2020 spacecraft, all kind of sort of disassembled at the Jet Propulsion Lab, NASA's Jet Propulsion Lab, which is in Pasadena, California. We often just refer to it as JPL. And it's in what's called a high bay. A high bay is a very large kind of warehouse room that is super clean. It's a clean room. Everybody in there wears these clean room bunny suits. Everything is sterile. One of the reasons for doing that is they don't want to contaminate Mars. You know, we're going there to look to see if there's any signs of past or present life. And what we don't want to have happen is for us to discover, yeah, there's life there. And then it turns out to be microbes from Earth rather than microbes from Mars. So they have to keep everything extremely clean and sterile. So this is the spacecraft before launch. It's partially disassembled in the high bay at JPL. And I'll just kind of talk about the different components that you see. Up at the top, you see what we call the cruise stage. The cruise stage has some solar panels on it to generate electrical power from sunlight. It has communications equipment. It has some rocket thrusters and fuel tanks to support those. And it is basically there to support the spacecraft while it is cruising from Earth to Mars. That trip is going to be a 6.5 month trip. And so the cruise stage provides the power and the communications and so on during that cruise. Just below that, you see what's called the back shell. The back shell is part of the enclosure that holds the sky crane and the rover. So the back shell is attached to the cruise stage, and inside will be the sky crane, which is what lowers the rover to the ground. And you have the rover itself. You can see its wheels here all tucked up inside. And then on the bottom of this is the body of the rover right here. And on the bottom of the rover is a little compartment where the helicopter is located, the Ingenuity helicopter. It's a little helicopter that they're going to fly around on Mars after they land. And then finally, down at the bottom here, we have the heat shield. The heat shield is made out of a special material that can withstand extremely high temperatures. When the spacecraft enters Mars' atmosphere, it will be going very fast, more than 11,000 miles an hour. And that will cause quite a bit of friction, which will heat up the surface of the heat shield well over 2,000 degrees. And so this heat shield is designed to withstand those kind of temperatures and protect the rest of the spacecraft and the rover. All right. So let's go back to July 30th, launch day. The spacecraft was launched from Cape Canaveral in Florida, and it was initially launched into what we call a parking orbit. A parking orbit is an orbit around Earth that allows mission controllers to check out the spacecraft and get it into the right position for the next phase of the flight. Now, the parking orbit velocity in the parking orbit is about 7.8 kilometers per second. That translates to just under 5 miles per second. You'll have to forgive me here. A lot of the stuff I'm going to be showing you is in metric units, so I'll try to translate when I remember to do so. So bear with me on that. Okay, so Mars 2020 is in a parking orbit, and the Earth is in an orbit around the sun. So the Earth is orbiting in this direction around the sun, and its orbital velocity is pretty fast. The Earth is moving at about 30 kilometers per second in its orbit around the sun. That's about 18 miles per second. And in order to get to Mars, the spacecraft has to leave the Earth going faster than the orbital velocity of the Earth itself. And so when the spacecraft was in the right position in its parking orbit, they fired its upper stage rocket, and that launched it into a trajectory away from the Earth, traveling, actually being in a solar orbit. So it went from being in orbit around the Earth to in orbit around the sun, traveling about 3.65 kilometers per second faster than the Earth is orbiting. So that's a little over 2 miles per second. Okay, so that trajectory puts it onto an orbit we call a transfer orbit. So this is what the spacecraft looked like as it was leaving the Earth. It's all buttoned up in this image here, but here again is the cruise stage. Here's the back shell. Here's the heat shield. And of course, the rover and the sky crane are inside this enclosure, right? So here's what things look like on launch day. This is the position of Earth and Mars relative to each other. They were actually fairly close to each other. Something I should mention is Earth and Mars do not orbit the sun at the same speed. The Earth orbits faster than Mars. The Earth takes 365 days to orbit the sun. Mars takes about 687 days to orbit the sun. So Mars is orbiting slower. So, at the point of departure on July 30th, they were actually fairly close to each other. And you might think, well, gee, we'll just take the straight line approach and head right over there. But unfortunately, doing that would take a huge amount of energy. You would have to get going very fast. And when you got to Mars, you'd have to spend even more energy to slow down to get into orbit around Mars or to land on Mars. So we don't want to do that. what we want to do is fly a trajectory that uses the least amount of energy. It's the cheapest way to go. And that's why we fly in these trajectories that are long arcing trajectories. We leave the Earth at about 3.65 kilometers per second. That puts us into this long arcing trajectory called a transfer orbit that takes us out to Mars's orbit, but it's kind of a leisurely pace. And so we arrive at Mars's orbit about the same time that Mars is there on February 18th of 2021, 3 weeks from now. And so this is where uh, Mars will be when Mars 2020 spacecraft arrives there. Now, remember I said it left the Earth going about 3.65 kilometers per second faster than the Earth. By the time it gets to Mars, it will have slowed down quite a bit. In fact, when it gets to Mars, it's actually going slower than Mars. It's going about 1.8 kilometers per second, which is about 1.1 miles per second, slower than Mars. And so you have to kind of time it so that you actually get out in front of Mars initially so that Mars can catch up with it. Otherwise, Mars would just buzz right by you. So at that time, Earth is a lot farther away from Mars than it was when on launch day. And it's about 202 million kilometers away, which works out to be about 125,611,000 miles away from Mars. So it's pretty far away. And if you were to go outside on February 18th and look for Mars in the night sky, you'd discover it's pretty low in the western sky after sunset. So that's where Mars is going to be, and that's how far away we're going to be from Mars on arrival day. Now that creates a problem for controllers here on Earth. When it's that far away, you have a little problem about how long it takes for a radio signal to go back and forth between Mars and the Earth. For 202,273,000 kilometers, it takes light or a radio signal almost 11 minutes and 19 seconds to get there. So we call this one-way light time. Radio signals travel at the speed of light. And so it takes a radio signal about 11 minutes and 19 seconds to go from the Earth to Mars. And if you send a signal to the spacecraft and you say, do this and tell me when it's done, you got to wait another 11 minutes and 19 seconds before you get an answer. So, it could be a 23-minute round trip. And when that happens, it's very hard to control a spacecraft. So a lot of what the spacecraft does has to be done autonomously. It has to do it automatically, relying on instructions that you've given to it days in advance. So it takes a lot of planning to do this. And there are a lot of steps, as you'll see here in a minute, there are a lot of steps involved in landing on Mars. And we'll see that here in a couple minutes. So this is a graphic that I did myself when I did all of the calculations for the orbital mechanics. I did a presentation on that a couple of months ago. Here's an image done by NASA, and this one's kind of rotated 90 degrees. So over here you see where Earth and Mars were on launch day, and here's where they are on arrival day. And this is the trajectory that they follow, that Mars 2020 follows. And you see several points along here called TCMs, TCM1, TCM2, and so on and so forth. TCM is an acronym. NASA likes their acronyms. And this one stands for Trajectory Correction Maneuvers. Although they try very hard to launch away from the Earth on a trajectory that's going to get them to Mars, it's not always perfect. So they have several opportunities during the flight to make minor adjustments to either the velocity or the heading of the spacecraft to make sure it gets to Mars and gets there at the right time and lands in the right place when it gets there. So several of these TCMs have already happened, but there's three more that are still coming up. And they don't necessarily do all of these, but they have up to three opportunities just before arriving at Mars to make some last minute corrections, including, remember how I said Mars is orbiting faster than the Mars 2020 spacecraft is? Well, they have to adjust for that when they get close to Mars. So here's another image. This shows where Mars 2020 was relative to Mars 1 week ago, last Friday, January 22nd. And this is a screenshot from an application that's on a NASA website. And you see the link down here. You can go there yourself and actually follow the spacecraft. It's called NASA Eyes. They have a couple of different versions. This one is Eyes on the Solar System. Uh, so you see where Mars 2020 is and where Mars is. Now, the first thing you notice is Mars 2020 is actually out in front of Mars. It's gotten out in front of it, but its velocity is slower than Mars. So Mars 2020 at that time was going at about 22.27 kilometers per second. And Mars itself was going a little bit faster, 23.9 kilometers per second. So, this is roughly about 14.2 miles per second, these velocities here. So that means that even though Mars 2020 right now is ahead of the planet itself, Mars is going faster, so it's going to catch up with Mars. In fact, the difference between the two velocities right now is a negative 1.63 kilometers per second. And the negative means that they're actually getting closer to each other. So that's just in terms of their relative velocities. In addition, you notice that the two orbits are converging, which means that you have an additional component there that makes the velocity relative to Mars itself actually faster than 1.63 kilometers per second. They're going to have to adjust that just prior to arrival at Mars, because you want to try to show up at about, say, 500,000 miles from Mars. You want to try to get there going almost the same speed as Mars is going in the two orbits. So they're going to have to make some adjustments to that when they get there. All right. So here's the Mars 2020 spacecraft about to arrive at Mars. You see the backside of the crew stage right here with all the solar panels. Those have been generating electricity for the spacecraft. There's thrusters on it. They've been making those TCM corrections. And as it gets close to Mars, they don't need it anymore. So when it's about 1,000 miles away from Mars, the cruise stage is going to separate from the spacecraft. Don't need it anymore, so we throw it away. Now, you notice in this image here, here's that Syrtis Major region that I was telling you about, and you see that the spacecraft is headed right for it. So cruise stage separation is one of the first events. That happens about 16 minutes before landing. As it gets closer, about 81 miles above the surface, it enters the atmosphere. And this is when the so-called 7 minutes of terror starts. When it enters the atmosphere, friction with the atmosphere causes that heat shield to heat up. It gets well over 2,000 degrees. The spacecraft is being buffeted because of variations in the density of the atmosphere. And the spacecraft is also trying to actually do a little flying in the atmosphere. So when it comes in, it doesn't come straight down, it comes in at an angle. And by slightly adjusting that angle and the orientation of the spacecraft, it can actually steer the spacecraft as it's descending down through the atmosphere. So it's at an angle like this, and it continues for quite a while, coming down lower and lower. And eventually it gets to a point where it's time to deploy the parachute. By this time, it's gone from about 11,000 miles an hour, actually a little over 11,000 miles an hour, down to about 940 miles per hour. Um, and it's about 7.5 miles above the surface of Mars. And that's where the parachute deploys. And that slows things down even more. And about 20 seconds after the parachute deploys, the heat shield, which is no longer needed, drops away. And then a little while later, the sky crane with the rover attached drops out of the back shell. The back shell drifts away, and the sky crane has 8 thrusters, which you can see right here. These 8 thrusters that basically fly the rover to its landing site. Now, there's some navigation equipment on the spacecraft that actually allows it to pick a good landing site. You don't want to land on a cliff. You don't want to land on a big boulder or anything like that. You want to land in a relatively smooth area. So there's actually software and a camera on the spacecraft, and it's going to do some navigation to get it to a good landing spot. Now I'm going to show you a little bit more about that in a second here. So the sky crane takes it down to just a few dozen feet. About, the sky crane is released from the back shell at 6,900 feet. When it gets down to about 6,200 or 62 feet, sky crane lowers the rover. So there's some cables. It lowers the rover on those cables. The wheels, which have been tucked up inside the sky crane, they drop down. Um, and it lowers it down and brings it down to the surface. There are some little devices on the where the cable's attached on the rover called squibs, and they fire and they cut the cables, and the sky crane then flies away, and it goes a couple hundred yards away, and it crashes and leaves behind the rover on the ground, ready for action. All right. So I mentioned a little bit about some of these steps here and how complicated it is. And I just have a graphic from NASA here, which shows all of the what I was just talking to you about, plus a lot of other steps here. So here it is out here. It's out in space, cruise stage separation. Uh, it begins to guide itself while it was in flight. There are some weights that are on the back shell which keep it balanced, because as it's flying, it's actually rotating, it's spinning. And so you want to make sure it's well balanced, like the weights on your car wheels to balance your tires. Well, those we don't need anymore. In fact, they actually would cause problems. So they get rid of those, and that allows the spacecraft to enter the atmosphere at an angle and basically fly through the atmosphere at an angle for a while until it's time for the parachute to deploy. When the parachute deploys, it needs to be more or less straight up and down when the parachute deploys. So there's some more weights that they get rid of just before parachute deploy. And it continues on down. And right in this area here, it starts navigating and actually starts steering itself toward a suitable landing location. And that's it's a system that's kind of interesting. It's new to this lander. What they do is they have some images taken by the Mars Reconnaissance Orbiter spacecraft, and that's stored in the sky crane. And uh, there's a camera on the bottom of the rover, and the camera is taking pictures of the ground, and the software is matching those pictures to the image that it got from the Mars Reconnaissance Orbiter. And it's using that to steer the spacecraft away from the cliff at the edge of the delta region there, and steer it towards a nice smooth landing area. So that's a new feature that we haven't seen before on any of these landings, and it'll be interesting to see how well it works. So that's the whole landing sequence. Here's a list of all these events that I've been talking about. You see there's a whole bunch of events involved. Now, like I say, this all has to happen automatically. Um, You can't communicate, you can't give directions to the spacecraft, so it has to be programmed to do all this stuff, figure out where it is, and do all of this stuff in the right sequence, at the right time, at the right altitude, at the right speed, and so on. And the poor controllers sitting back at JPL and NASA, they don't have any control over it. All they can do is monitor what's happening and wait for the signal that says, yes, that event has happened and that next event has happened and so on until it finally lands. So it's a pretty high tension situation. And that's why they have the term, the 7 minutes of terror. The 7 minutes actually starts at atmosphere entry right about here. And from then on, it's just keep your fingers crossed and hope everything works right. Now, one of the things I like about NASA is there's a lot of guys there who have a good sense of humor. And so there's an event in this process that I wanted to call your attention to. It's called SURFER or SUFER. And SUFER is actually an acronym that stands for Straighten Up and Fly Right. Now, that sounds like a funny term, but it's actually what the spacecraft does. It has been coming down through the atmosphere with the heat shield protecting it. It's getting bumped around and everything. And by using the shape of the spacecraft as what we call a lifting body, it can actually steer, but it has to do that with the spacecraft at an angle relative to its descent through the atmosphere. The SUFER maneuver, the straighten up and fly right thing, they eject some additional weights, which causes the spacecraft to turn. So it's up and down. So this heat shield is facing down, the back shell is facing up. And it's then that the parachute can deploy. So I always think it's funny that they call it straighten up and fly right. All right. Okay, so I've gone through the whole landing sequence here. I'm sure you've all been taking notes and you're now experts on it. But just in case, rather than listening to me give all this detail, I thought it'd be cool to watch a video. NASA has created a video showing this whole sequence. They've speeded it up quite a bit, so it's not a 7-minute long video. So if you'll bear with me for just a second here, I'm going to share my screen and we'll show you the video. Okay, so watch this. At first, there won't be very much sound, but that'll change after a few minutes. So bear with me here while we run this. So February 18th, spacecraft is out in space. It's working its way toward Mars. And here it comes. By the way, there's no noise out in space. All right, so the first thing that happens is you lose the cruise stage. Then it orients itself to enter the Earth's or the Mars's atmosphere, where the heat shield heats up, and it's losing velocity. It's traveling over 11,000 miles per hour when it enters the atmosphere. Of course, the spacecraft is nice and snug inside. There's Jezero crater. Drifts for a while and then it'll lose the heat shield. There goes the heat shield. There's the sky crane. crane flies away and it crashes somewhere off in the distance. There's the rover, all ready to go. Well, not actually ready to go. They still have to do a lot of testing once it's on the ground. They have to raise the mast, extend the tool arm, and get to work. And you can see in the background in this image, you can see the cliffs at the edge of that delta region, which is the area of interest. And you can see a hint of the river that was once flowing into the crater. And so this is the whole sequence, a very short version of that whole sequence. And it gives you an idea of what's going to happen. And again, all of that happens automatically while the controllers on the ground at NASA just sit and watch and keep their fingers crossed. All right. Okay. So that's the whole process. That's what we have to look forward to. Again, we're going to be following that on the February 18th, starting at about noontime. So I thought, well, now would be a good time. If you want, you can start submitting some questions. Jessica is going to join us here again, and she's going to be reading the questions. Whoops, I didn't want that one. Stop the share. I got one more slide here to show you. Because, you know, it's question time. So here's our friend Gort, who's going to answer all your questions for you. Okay.
Wonderful.
All right. So, Jessica, you're on.
All right. So we've gotten a few questions that have come through.
Okay.
First one is, will the rover return to Earth at any point? And if so, how will it, considering the fact that they got rid of pieces of the spacecraft?
The rover will not be returning to Earth. Rover is going to stay on Mars. It will probably be on Mars operational for several years. The intent, the design life is 1 Martian year. Again, a Martian year is 687 Earth days. Days on Mars are called sols, not days. And a sol is actually slightly longer than an Earth day. An Earth day is 24 hours long. A sol is 24 hours and 39 minutes. But the intent is for the spacecraft or the rover to stay operational for at least 1 Martian year, 687 Earth days. Now, if it follows the same example as the other rovers, it's going to be there for a lot longer than that. And it'll still be operational for a lot longer, but it will never return to Earth unless somebody goes up there and gets it. All right.
All right. Another question is, how long is the rover expected to operate on Mars?
I think I just answered
that. Oh, sorry. Okay, moving on.
So design life is 1 solar or 1 Martian year, 687 Earth days, but it conceivably can last quite a bit longer than that. You know, all of the other rovers that we've sent up there have lasted a lot longer than they were originally intended to run. You know, the Curiosity rover is still going. It landed in 2012 and it's still going. I expect that its Perseverance is going to be still operational several years from now.
All right, thank you for that. All right, so does the helicopter have a self-guided pre-programmed flight plan, or will there be human manual intervention, taking the possible command delay into account?
Okay, because of the long time delay, they will not be able to fly the helicopter manually. It will be programmed to do certain things. So it won't start flying until several days after the landing. You know, they have to do a lot of checkouts with the rover itself and everything, but eventually the rover is going to move to a position where the ground underneath is nice and smooth. The helicopter will be dropped out of the bottom, and then the rover will move out of the way, and then the helicopter will make a number of pre-programmed flights around the rover, around the area, and will be transmitting its signal back to the rover, which will then in turn transmit whatever the helicopter is seeing up to a relay satellite that's orbiting Mars and then back to the Earth. So it's all going to be autonomous.
All right. And how close is the Perseverance rover to the other rovers that are already on Mars?
Actually, it's going to be pretty far away. The other rovers, there's three, actually, now there's four rovers that are on Mars. The original Sojourner, uh, the Spirit and Opportunity, and the Curiosity rover. And they're all in different locations. So they're all kind of spread around Mars. So they're looking at different parts of Mars with each of these missions. So pretty far away.
The next question is, how are we going to get the Mars samples back here on Earth?
Another spacecraft in the future, probably sometime in the 2030s, will fly to Mars and actually retrieve the sample cache from the Curiosity rover and will fly it back to Mars. Exactly how they're going to do that, I haven't really seen too much data on that. It's still, I think, a little fuzzy, and I think they're still trying to figure out how they're going to go about doing that. But they do plan to eventually retrieve those samples and bring them back to Earth.
All right, we've got lots of questions coming in.
Okay.
Um, why does the delivery vehicle lose velocity in transit to Mars in empty space with no friction?
Well, it's actually something you can demonstrate yourself. If you take a ball and you toss it up in the air, it goes, it leaves your hand very fast, but as it goes up, it slows down and eventually stops and comes back. We're doing kind of the same thing, sending that probe to Mars. It's launched initially from Earth. It's got a lot of velocity, but it goes out, it goes farther away from the sun than the Earth is. And as it's going farther away, it's losing velocity. The sun's gravity is trying to pull it back and pull it back, just like the Earth's gravity is trying to pull your ball back when you throw it up. And so the spacecraft slows down. Now, if Mars, for some reason, it got to where Mars's orbit is and Mars wasn't there, the spacecraft would keep going in a long arc and it would actually stay in orbit around the sun. And that orbit would bring it back to the same point where it left Earth. Of course, the Earth wouldn't be there at that point, but it would go into an orbit around Mars faster when it's closer to the sun and I'm sorry, orbit around the sun, and it would be faster when it's closer to the sun and slower when it's farther away from the sun. So that's just part of orbital mechanics. That's how it works.
All right. Are the Perseverance solar panels sheltered on landing and then open spread after landing?
Actually, Perseverance does not get its power from solar panels. Perseverance gets its power from something called an RTG, radioisotope thermal generator. It's a little nuclear reactor, if you will. It has some plutonium pellets inside of it. And plutonium is subject to radioactive decay, and as it decays, it generates heat, and that heat can be used to generate electricity. And so uh, both Curiosity and Perseverance use an RTG to generate power. So they can operate day and night. They don't need to worry about solar panels getting dusty or anything like that. They've got a kind of a constant source of energy. And that RTG system will last for years and years and years. It'll actually probably outlast the rover.
What is the top temperature for the heat shield?
Well over 2000 degrees. I don't know what the maximum temperature is, but I do know it's well over 2000 degrees.
All right. And then there's some questions about the satellite that's going around Mars. How long has it been there? When was it sent there?
Oh gosh, Mars Reconnaissance Orbiter is one of several satellites orbiting Mars. I want to say it's been there for about 10 years, but don't quote me on that. So sorry about that. I don't remember off the top of my head how long it's been there, but I know it's been there quite a while. It dates back. I actually worked on that spacecraft back when they were building it, and that's was I would say mid 2000s. So it's been there for probably close to 10 years now. I'm sure somebody will look it up. You know, so-
Yeah. We have some questions about the flight, animation video that you shared. Is there a place that people can find that online?
Yes, yes. You can go to, there are a couple of websites that have it. NASA has several websites dedicated to the Mars 2020 mission. And I can't remember which one I found it on, but there is one where it shows the whole landing sequence. Um, and I wish I knew off the top of my head what the URL it was. But if you Google Mars 2020, NASA Mars 2020, and hunt around, you should be able to find that video. There's actually a couple versions of it that they have.
Thank you, Joe. Let's do a few more questions. We have some more time.
Okay.
Um, you may have mentioned this, but was there a certain reason that NASA chose the intended landing location of the Perseverance rover?
So the landing site is Jezero Crater, which I showed earlier. And the reason they picked that was because it had that delta where they could see that material had flown or or had come down an old river and flown into the what was once a lake inside the crater. So that's why they picked it, because they think there's a higher probability that there may be signs of past life at that location. You know, one of the questions that was asked here was about where the spacecraft is going to be relative to other uh, spacecraft that have landed on Mars. And I've got an image here that I think I'll share with you if you don't mind. So this is kind of a flat map of Mars, and you see where all these different spacecraft have been, all the landers and all the rovers have been. This is Certus Major. This is where Perseverance is going to be. This is Opportunity. This is Pathfinder, the original Sojourner rover, the first one on there. Opportunity. Curiosity is right here. Spirit is over here. Uh, so you see that they've kind of spread out, and they're trying to cover as much of Mars as they can with all these different missions in order to study different terrain, different soil types, and so on. All right.
All right. And then do you know what the material that the parachute is made of? Someone that looks very different than Spirit and Opportunity's parachutes.
It's actually very similar to the Curiosity parachute. I don't know off the top of my head what the material is. It's probably a very heavy duty synthetic fabric of some kind. Um, I know they had a lot of trouble designing that parachute because initially, no matter what they seemed to do, when they tested the parachute, it would collapse on them. And eventually they realized that they had to uh, cut holes in the parachute, slits in the parachute in certain locations in order to keep it inflated while the spacecraft was coming down. But I don't know what the material is. You know, I've got a image here, I think somewhere of the parachute. See if I can share that here. Okay, so here's the parachute. It had to have a hole in the center and it had to have these slits around the side in order to keep the parachute inflated as it was coming down in that very thin atmosphere. Uh, and what it was made of, I'm not sure, but I'm sure that's something. If you search around on one of the NASA sites, you can find out what that material is.
All right. I think we have time for a few more.
Okay.
Um, let's see. What biomarkers can be searched for that would be considered indications of life?
Well, if we found any kind of chemical process, that would be an indication of life, especially uh, present life. If you find that nutrients are being used up, if methane is being generated, anything like that. Uh, you also look for actual physical structures. Back in the 1990s, there was a period when NASA had thought they had actually found evidence of life on Mars. Some scientists at the Johnson Space Flight Center in Houston were looking at some meteorites that actually had come from Mars. And when they cut into them, they found these short, little, long things that looked like bacteria, except that they were fossilized. And so there was a lot of speculation that that might be an indicator of life. Since then, there has been a lot of research that suggested that might have been some other more natural process. But it's those kinds of things that they'll be looking for on Mars to see if they can find anything that indicates life, a fossil, a structure that looks like it formed from a life process, anything like that that they can find. And again, testing the chemistry as well of the soil and rocks to see if there's any processes there that they can definitively attribute to life.
All right, I think we have time for one more.
Okay.
What happens to the top space guidance part of the spacecraft after it detaches from the lander?
So the back shell actually is still attached to the parachute. They drift off and eventually land on Mars somewhere else. One of the cool things that they try to do is after it's landed, they try to find it. So that Mars Reconnaissance Orbiter spacecraft has some pretty high resolution cameras on it, and they will should be able to find the parachute and the back shell. Uh, it may be a few days afterwards, but they may actually be able to photograph it on the ground on Mars. Um, and another thing that they may be able to do is actually photograph the spacecraft as it's coming down on the parachute. When the Curiosity rover landed on Mars in 2012, it basically was very similar process. And as the rover was still attached to the back shell, and the back shell was suspended from the parachute and coming down, the Mars Reconnaissance Orbiter was actually able to find it and take a picture of it. And there's a picture, I've seen it several places on the web, where you can actually see the parachute and the back shell as it's drifting down while it was landing. Right?
All right. Well, I wish we had some time for more. I know there's more questions coming in, but if anyone has more questions, we'd be happy to get back to you via chat. And thank you, Gerald, for your
Okay.
time this
Well,
evening.
and the other thing you can do is write those questions down. And on February 18th, starting at noontime, we're going to be covering the landing. We're going to actually do some live coverage. And that's a great time to ask those questions that you've thought of. So, hang on to those questions. We'll get at it then. We'll have lots of time to cover questions.
Absolutely. Thank you, Gerald, for mentioning that. Definitely be sure to tune in with us. It's going to be a really exciting time. We'll be tuning in at 12 p.m. on February 18th. The landing set to be between 12:30 to 12:55-ish, but we want to get started early. We'll be tuning into NASA TV, and then we will head into a Q&A at the end. So that will be a really exciting day. Definitely bring your questions for that. And thanks again, Gerald, for joining us. This
You're
was a
welcome.
really fascinating talk. I'm so excited for February 18th to watch this happen. And had a lot of fun learning tonight, and I hope you all did too. And coming up, we hope you'll also join us tomorrow night and every Saturday for our virtual telescope viewing with Gerald and Richard and team at 9 p.m. And hopefully we're looking at some good stuff tomorrow night. And for notifications about our events and more fun science content, please visit our website at chabotspace.org. Thank you, everyone, for who tuned.
And hit that donate button.
Yeah, thanks,
Yes,
Gerald.
please.
Yes.
Yeah.
Thank you, everyone who
Right.
tuned in tonight. Special thanks to our members, donors, and partners for helping us bring science to life for everyone at home. Like Gerald mentioned, consider making a donation to us at chabotspace.org or right here on Facebook. Right now, we need your help to create STEM learning opportunities for our community at home, and we appreciate your support. Thank you, everyone, again for joining us, and we hope to see you next time. Have a good evening.